Welcome to Sigma Solver guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to look at another topic in the modeling and simulation playlist. So let's read the question first. In a fish farm, fish are harvested at a constant rate of 2100 fish per week. The per capita death rate of fish is 0.2 fish per day per fish, and per capita birth rate is 0.7 fish per day per fish. Write a word equation describing the rate of change of the fish population. Hence, obtain a differential equation for the number of fish. Second, if the fish population at a given time is 240,000, give an estimate of the number of fish born in 1 week. Third, determine if there are any values for which the fish population is in equilibrium, means the birth rate and death rate are same. Fourth, write down the numerical algorithm to simulate the problem using specific parameters. So this problem is clearly regarding compartmental models, which is a big section in modeling and simulation. So we'll understand it step by step. Compartmental model for fish population, part 1, forming the differential equation. So first we take Pt, which is the fish population at time t in days. So since this problem is more towards the language, so we'll be very specific in the terms we use, that is what t exactly means. So whether it's in seconds or minutes or days. So in this instance I am taking this in days. Next, birth rate per capita, which is 0.7 per day per fish, and death rate is 0.2 per day per fish. Now harvesting rate which is given is 2100 fish per week, which boils down to 300 fish per day. The rate of change of fish in population can be understood in this particular equation. dp by dt, which is the rate of change, equals number of births minus number of deaths minus number of fishes that are harvested, all with respect to the unit of time that we discussed above. So birth term is 0.7 pt, death term is 0.2 pt, and harvesting term is 300, which is fixed and is not dependent on the population in the fish farm at that time. Next, we go to find the differential equation which we can derive out of these information points. So dp by dt equals 0.7p minus 0.2p minus 300. So we simply find that out, 0.5p minus 300. So this particular equation that we get is the numerical representation of the word problem that we were supposed to find in the first part. Now let's go to part B. Estimate the number of fish born in 1 week. So given population is 2,40,000, births per day is obviously 0.7 times the population, which is 168,000. Births per week, since this was per day as per the rate, now we want to find it per week, so we simply multiply it, which comes out to be this much, right? Next, we find the equilibrium population at which the death rate is equal to the birth rate. So at equilibrium, dp by dt equals to 0, and therefore if we take the equation from part A, which was 0.5p minus 300, and put it here, it should be equal to 0. So p comes out to be 600. This is the fish population in the fish farm at equilibrium state. Next, we find the numerical algorithm using Euler's method. So if you guys want to know how Euler's method is applied mathematically, I'll link a video here in the I button and you can check that out. To simulate this problem, we'll initialize the parameters first. So p0 is set to a particular number, let's say 30,000, and then set a small step, that is delta t, example 1 day, and then set the simulation time. I mean, what is the end time at which the simulation will stop? Let's say time equal to t equal 15 days. So what is the population after 15 days of start of the fish farm, right? Next, we iterate using the Euler's update rule. So Pn plus 1 equals Pn plus delta t times of the given equation, which is dP by dt. So we take that. Now we repeat until the simulation ends, which is t reaches 15d, right? So what I've done here is I have made the Python code, and we'll do a code analysis for that as well. So we import the basic libraries NumPy and Matplotlib. Then we define these parameters. So let me zoom in a bit. So P naught is the initial phase population, dt is the time in days, and t is the total simulation time. So in this case we are taking 100 days, and we'll also need the number of iterations that we are going to do, which is stored in n. That's why I am dividing t by dt. So let's say if it had been time step was 2 days, then the number of iterations would have been 50, right? So next I just have defined it to store all zeros for now, and P0 needs to be defined as P0, right, because it is the initial population. Then we take the Euler's method for I in range 1 to n. Pi equals Pi minus 1 plus dt times 0.5 times the previous population number minus 300, and then we plot the results using the plt.plot function, right? We take the x label as the days and y label as the population. So that's how you can use compartmental model to analyze a real world problem, as well as use Euler's method in a Python program to visualize the population graph and the impact it has due to birth rates, death rates, and so on, right? So that's been it. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.